So, Jai Hind, my name is Ritesh Sharma. I am from Ajay Kumar Garg Engineering College, Ghaziabad, and I am taking the subject Fundamental of Electrical Engineering in first year. The subject code is BW101. So, today I am going to take a topic from unit number 4, the three-phase induction motor. So, today in today's this lecture, we will cover some few important topic like the principle of three-phase induction motor, the production of rotating magnetic field RMF, slip and its effect. So, these are the topics or the contents of today's lecture. So, let us start with the working principle. So, we know that in a three-phase induction motor, since it is a three-phase motor, it has a stator and rotor, three-phase stator winding and a three-phase rotor winding. So, in the three-phase stator winding, we have the winding is star connected or delta connected, and these star and delta connected are 120 degree electrically apart. So, these the overlapping of these windings in a stator slots are electrically by 120 degree. So, according to the Faraday law, whenever the EMF induced in any circuit is due to the rate of change of magnetic flux through the circuit. So, as the rotor winding on the rotor side is short circuited, there will be a flow of current, and because of when the current carrying conductor placed in the magnetic field, it will experience a force. This is the law. So, your rotor gate started and it will rotate. So, this is the basic principle for the three-phase induction motor. Now, in which direction your rotor will rotate? It will be decided by the Lenz's law. The Lenz's law says that the cause opposes the effect, and the rotor will rotate accordingly where it will oppose the cause, which is the relative motion between the stator rotating flux magnetic field and the rotor speed. So, it will try to oppose it. So, that difference will be reduced, the relative motion will be reduced, and the rotor will try to rotate in that direction. That means in the direction of rotating magnetic flux. So, this is the working principle of three-phase induction motor. So, we can say that with the help of this principle, that the rotor speed should not reach to the synchronous speed. Can our rotor rotate at synchronous speed? That speed, synchronous speed, will be given by, as we know that is 120 F by P RPM. So, this is the speed of the synchronous, or you can say it's a synchronous speed at which your field is rotating or stator field is rotating. So, can our rotor rotate at this speed? So, if the rotor will rotate at this speed, there will be no induction, because there will be no relative speed. So, no induction. So, no current will flow, and there will be your induction will stop, and your rotor will again come at the speed lower than the synchronous speed. So, you can say that your rotor cannot attain the synchronous speed. It will rotate at less than the speed of the synchronous speed. This is the basic principle. Now, as the rotor cannot reach the synchronous speed, the difference between the stator and the rotor speed is called the slip. Now, if the rotor cannot attain this speed, so there is some difference. We call it the slip speed. That is called slip, is a term, is called ns minus n, where ns is called the synchronous speed, that is your the speed of the rotating magnetic field, and n is the speed at which your rotor is rotating. So, this is called the slip speed, and the percentage slip is given by ns minus n with respect to ns into 100. So, percentage slip is given by this formula. So, this is called the slip or slip speed. Now, after this the basic principle of working principle of this three-phase induction motor, let us understand the production of rotating magnetic field, how this rotating magnetic field is produced. So, for this, first of all, when the three-phase winding is energized from a three-phase supply, when the three-phase winding, stator winding, which is a star or delta, when it is energized from the three-phase supply, a rotating magnetic field is produced. This is what we are saying. So that it means that is field will rotate at synchronous speed, that we all know that. That means the poles on the stator, they are shifting their position, you can say in that way. So that means this is called the rotating field. Now let us investigate this, how this rotating magnetic field is produced. So for this we have the three phases winding. On the stationary part we call the stator, and this three-phase stator winding is connected in star or delta. We know that the three-phase winding is connected in either star or in delta. So the three-phase winding are displaced from each other by 120 degree, or they are displaced by 120 degree. So here, if the three phases are displaced by 120 degree, that means the three phases, if we called it that phase R, Y, V, which is the standard nomenclature. So flux in the R winding or first, and the flux in the Y phase, and the flux in the B phase. And you can see that these fluxes are displaced by 120 degree. Suppose that if we draw this is the phase, the waveform, that is the phi R, that is the R flux, which is a sinusoidal, then Ry, which is lag by 120 degree, so after 120 degree, and then flux B, which is lag by 240 or plus 120 degree. So that is here in this stage. So this is the three fluxes. These are the three fluxes in the three-phase supply. So if you draw the phasor diagram of this, suppose that we take this Y and phi B, which is omega t or lag by 240 or lead by 120 degree. That is a B, phi B. So you can see that these three fluxes are displaced by 120 degree. That means they are a symmetrical supply. That is a balanced supply. The three fluxes are equal in magnitude, and if they are displaced by 120 degree, that means they are symmetrical or balanced supply. And this is the phasor diagram, and this is the waveform of the three fluxes phi R, phi Y, and phi B, which is displaced by at 0 degree. At 0 degree, when we take the omega t is 0 degree, at 0 degree at this position, that is when theta is equal to y, phi y is minus of 0.866, means its value is negative of this. So you can say that its phasor will be, if I take the same color, the phi r is almost 0, it is 0, that's why it is taken dash. Then phi y, that is a y phase, which is negative of that. So negative of that means it is like this. That is called minus 0.866 phi m. And phi b, that is the flux in the B phase, is plus 0.866. So plus means in that same direction. So this will be given by plus of this. So 0.866 phi m. And if you take the resultant of both, that will be something like this, and this is the resultant. The resultant, that is phi r. So phi r can be calculated. Suppose this angle will be 30 degree. This angle is it's a 30 degree. So from this word, this is 0 O A B and C. So when you if you have to calculate the resultant value, that is phi r, then you can take the cos 30 degree. Cos 30 degree will be equal to OA upon OC, where OA is equal to half of OB upon OC. And OC, the value of OC is this, root 3 by 2 phi m, and OB is equal to the resultant flux, the phi r upon 2 upon root 3 by 2 phi m. And cos 30, we know that the cos 30 is given by root 3 by 2. So root 3 by 2 will be equal to, from this, phi r upon root 3 into phi m. So this phi m will be go over here. So root 3 into root 3, 3 and 3 by 2. So resultant flux will be equal to your 1.5 times of phi m. And its axis, the direction of axis is vertically upward. So this is the resultant flux. So you can write here the resultant flux will be equal to 1.5 times of phi m, and its axis is upward. You can see its axis is upward. At this, theta is equal to, or omega t is equal to 0 degree. So this is the first case that we have taken. Now in second case, when omega t is equal to 60 degree, when omega t is a 60 degree, let me when omega t is equal to 60 degree. For omega t is equal to 60 degree, we have calculated that the different value of flux at this instant. At this instant, that we have taken, at which the theta is equal to 60 degree or omega t is equal to 60 degree, at this instant when the theta is 60 degree, you can say that the value of flux r is 0.866, that is plus, so phi r. Okay. So in case 2, if we draw the phasor diagram when omega t is 60 degree, that is phi r is equal to, this is the phi r, this is the phi r, the phi r is equal to 0.866 phi m, and the phi y is minus of this, means it will have the negative of that. So minus 0.866 phi m. This is the phi m, and if you take the resultant of both, here the phi b is 0, so it will be like this. This is the resultant flux. Now you can name them. It is O, A, B and C. So this angle is 30 degree. So when you write cos 30 in O triangle OAB, in triangle OAB, the cos 30 will be given by, that is OA upon OC. So okay, so again you will find that the resultant flux will be given by 1.5 times of phi m. So you can write here phi r is equal to 1.5 times of phi m, but its direction is like this. So in the first case it was in vertically upward. Now when we shift the 60 degree, have taken the 60 degree, again the axis is shifted by 60 degree. You can see they shifted by 60 degree. In the next case, when theta is equal to 120 degree, when theta is equal to 120 degree, the phi r is equal to this. So phi r we have taken is 0.866 phi m, phi y is 0 and phi b is negative. So minus of this, so we will take the minus of phi y, that is something here, minus of 0.866 phi m, and the resultant of both will be given by this. This is the resultant, phi r, and this angle will be 30 degree. So again you will take the cos 30. So this is O, this is A, this is B, this is C. So in triangle OAC, cos 30 degree will be equal to again OA upon OC. OA is equal to half of OB, which is phi r upon 2. And when you calculate, the resultant flux will be equal to 1.5 times of phi m. So you can say that every time when we calculating the resultant flux, it is 1.5 times of phi m. This is the value of the resultant flux. And again when we calculate for the next 180 degree, 240 degree, 300 degree, again and again of 1.5 times of phi m, and it is rotating in clockwise direction, in this direction. And the speed, again we have already taken that the speed is given by ns, which is 120 f by p, which is 120 f by p is called the synchronous speed. So this is the rotate speed of, this is the how the resultant field is rotating, the rotating magnetic field is this. So the speed is ns 120 f by p, which I just told you in rpm, at constant speed and magnitude is this, and this constant speed is basically depend upon the frequency and the number of poles. Frequency and number of poles. What is the important point is the direction of rotating magnetic field. How this direction of rotating magnetic field can be changed. So that can be changed. It depends upon the phase sequence. The phase sequence of supply. If the phase sequence is RYB, suppose that if the phase sequence is RYB, so it is rotating in clockwise direction. If we change the phase sequence RBY, or if any terminal, if we replace any two terminals, then its phase sequence will be changed and it will rotate in the opposite direction. So this is how the direction of the rotating magnetic field can be reversed. So this is the basic concept for the three-phase induction motor. Why this? How this rotating magnetic fields can be developed. And the slip, as I told you, the slip is given by it is the relative speed between the or the ratio of the relative speed between the synchronous speed and the motor speed with respect to the synchronous speed. So when your motor is rotated at speed ns, suppose, so at this time its value will be 0, and when your rotor is at standstill, that is n is equal to 0, the slip will be equal to 1. So this is the when the rotor is stationary, that is s is equal to 1 or 100% slip is this. So this is the some basic concept of the three-phase induction motor. In the next lecture, we will discuss about some more important topics like the effect of the slip on the rotor parameter and the torque on the rotor. So thank you so much. Jai Hind.